Namaskar, welcome back. So, last lecture we discussed about uh, the faulting taking place in different environment, and then we stopped somewhere talking about the imbrication of imbricated faults and all that. Okay. Now, if we look at overall deformation pattern in compressional tectonics, then mostly we will come across the landforms like anticlines and synclines. And this was the basic part which one can uh, gather at the initial stage talking about the tectonics part. Okay. So you will have anticline, syncline, and then compression which is going on will result into the aligned deformational landforms in the region. Okay, where we can see also that the faulting will also occur. Now, in a very general form, if we take the stress and strain diagram, then we see that every material will deform first in the elastic deformation pattern, and then ductile, and at some location you will see a sort of an permanent strain which has been developed, which is irreversible. And finally, uh, after the ductile, what we call the brittle deformation, we will see faulting or fracturing. Okay. So, deformation of rocks under tectonic stresses, that how we can see. Okay. So, basically, if we look at and we as we are interested in the earthquakes and comparing the stress and strain pattern, so the final brittle deformation uh, is your faults is a fault slip, or we can say that is an earthquake. Okay. This part we have discussed in one of the lectures, that how this orientation of principal stresses will be uh, observed in different tectonic environments. You are having compressional tectonic, then extensional tectonic environment, and then strike slip environment. Another important part is that what will be the surface expression of or what will be the surface expression during different uh, faulting environment. So, in case of your extensional tectonic environment, what we call the tension, then in that case you will see a sort of an thinning up of the crust, and that will be because of the stretching effect. Okay. And in another case where we are having the compressional tectonism, where you have the deformation, or you can say the compression is going on from both the sides. Okay. In that case, you will see a sort of an shortening of the crust. Okay. And shortening of the crust, as at the same time what you will see folding of the material. And this process what we were talking about, that it will be first you will have it, if you see the stress strain diagram, then it will first have, and then finally it will, so elastically it will deform, the material will deform. Okay. And that is your thickening of the crust will also there, and here we are having thinning of the crust and the deformation. Final one will be your normal faulting environment. So this part we have discussed in the previous lecture also, that this is your hanging wall and this is your foot wall. In this case, you will enter into the reverse faulting, and this is your hanging wall, okay, which is going up, and this will be your foot wall, which is a stationary wall in both the cases. Okay. Then third environment, what we call the strike slip, is your shear. Okay, where you shear the your crust. Okay, so shearing is taking place, and then we also had discussion in the previous one that either it will move along with this component, that is normal component, or it may move up with the reverse component, okay, along the strike. So shearing, or we can say twisting laterally, and this will have result into the bending of the crust horizontally. And finally, at this point you will have the slip. Okay. So these are uh, three different environments which we have also discussed, and partly we have discussed about the compressional part. So let us move ahead in what we see in terms of the faulting. So this is a typical strike slip, okay, where one plate has moved, or the block has moved this side here and another has moved away from it. Okay. So if you are, as we were talking about, that since this plate is moving towards us, okay, because if you see, if you are standing here or any on the other side also, okay. So if you are standing here, then you will see that this is coming towards us, okay, and then another plate is moving away from us. Okay, so this is moving away from us. Okay. So this is typical of a right lateral strike slip, because this is coming towards us. Okay, so this is a right lateral strike slip. Then we already discussed this will be normal faulting environment. And then finally you are having the third one is the thrust or reverse faulting environment, where the hanging wall has moved up, okay, along the fault here. So this is your fault. And then third one is again a reverse faulting or thrust faulting, we can say, but the deformation has not reached right up to the surface. Okay. There is no clear cut slip as we see here. Okay. So if we compare these two layers here, or the sedimentary units or any units, then this has been displaced. Okay. So you have a sort of what we call the net displacement over here. So this will be your net displacement, because we are taking the lower bounding and the lower bounding there, or you can say that the upper bound and the upper bound over here. Okay, so this will be your net slip. So here you see the slip, okay, in the deeper portion, but when you move towards the surface, then you don't see any deformation, okay, any slip, sorry. So you have only the folding which is taking place, okay. Anywhere the surface is get warped, okay. So there is no displacement over here, no displacement, but of course there is a deformation, and this deformation has resulted into folding near surface. Such type of deformation, though it is in the compressional tectonics, we say this as a blind fault or blind thrust, because these layers are not deformed, the top layers are not deformed, okay. No displacement. Deformation is there, sorry, but no displacement has been seen by the surface, okay. Hence we call this as a blind thrust, okay. And then finally, as we have discussed in the previous one also, that you may have that what we were calling talking about, that 1+3 environment, where this is your uh, normal faulting and this is your strike slip, and here you have 2+3, okay. So you have reverse faulting and then you have a strike slip. So in one case, what has happened, if you put the vectors here, then the block has moved like this, okay, that is laterally, as well as the block has moved down, okay. So you have this two set of displacement, and in this case what you have is that block has moved up, okay, as well as the block has moved in this direction. So, this in reverse as we have discussed here. So, this is reverse plus strike slip and this is normal plus strike slip. Okay. And such faulting, if we come across or the deformation, then this we term this as an oblique slip faults. Okay. Now, what is an active fault topography? Because this is this part we will be talking about in, of course, we have discussed this in the normal faulting environment also, a part little bit that a scarp is formed and then you have the degradation and all that. Okay. But earthquake is caused by rapid movement of the fault in the subsurface. Okay. The rupture or the displacement in the subsurface often reaches the surface when the magnitude is generally above 6.5 or so, but it has been observed at number of places in the recent tectonic deformation wherever it is going on, that even 6.5 can result into the surface rupture. But mostly it has been seen that large magnitude earthquake will rupture the surface. Okay. The fault that reach the surface is termed as active fault. Okay. So, in previous lectures we have been talking about that how your degradation will take place. Okay. That we were talking about the fault scarps and all that. Okay. So, this final topography what we see uh, with the displacement. Okay. So, that will be your active fault scarp. This is in the normal faulting environment. Okay. We are talking about because the block has moved down along the fault here, but in case of reverse fault again we will have this topography. Okay. Now, there is like many papers that suggest that if the magnitude is higher or larger, then we will have clear cut surface deformation. Okay. And if the magnitude is intermediate, then we may have fault scarp within very low topography and may get eroded or we can say obscure. Okay. But if you are having large magnitude earthquake, then of course that large magnitude earthquake, because larger energy is been released. So, it may result into the greater displacement in terms of the larger earthquake, and that can result into the surface rupture. Clear faulting you will be able to see. Intermediate you will have, of course, the displacement will be comparatively lesser and the rupture may be seen, but that can be eroded because of the erosional processes when the scarp after the earthquake has been exposed to the weathering processes. Okay. But in case of the blind and small magnitude earthquake, that what we were looking in one of the slide previously, will see no surface faulting. Okay. Deformation is there, but no surface faulting. So, this is again this from this is an active fault here, which you see the topography. This is the topography here, and then fault runs. So, this is a fault trace. Okay. This is the fault trace, and what you see the topography. This is your fault topography. And finally, what we are looking at is this one is your fault scarp. Okay. This is your fault scarp. So, this is from US, where of course this block has moved up and this is down. Okay. This is from Indian side, from Punjab Himalaya, where so previous one, this is a normal fault, looks like normal faulting environment. Okay. But the second one is your reverse fault. Okay, this one is your reverse fault. So this is an, you can see this is reverse fault. So this is your, we see is the hanging wall, and this is your footwall, and then fault runs somewhere over at the base of this one. So active faults, if we define them, then it says that along which the movements have occurred in last 10,000 years, likely to occur in near future, and third point, that it is the manifestation of the crustal deformation, the displaced landform on earth surface. And this information is been considered to be a source for large magnitude earthquakes in near future, and it is very vital for the seismic hazard assessment of any region. Okay. So active fault maps, okay, should be very precise and are important. Okay. So initial proper mapping is very much important for your seismic hazard assessment. And this, of course, the information along with the active faults, this, because this and this we will be talking about the topography, but later we need to do paleoseismic investigations. This is important because this will tell you. So this we can do is based on the surface expression. That is what we are talking about, the geomorphology. But this we are going to do this, the trenching, and look at the signatures preserved in sediment, or you can say sediment section or say exposed sediment section, or in exposed stratigraphy. We will move further and then see if how different faulting environments we can identify the topography here. Now, active fault capable and potential, or we can say the potential active faults, you can classify this active faults also, but this can be done only after you do the paleoseismic activity investigations. Okay. So, classification of active faults. Around the world, scientific and engineering studies are conducted with an aim to locate, study, and characterize the surface rupturing faults. Okay. But here the characterization, we are not using the seismic data, that is the earthquake epicentral data. People also try to characterize this, but this is not exactly what we are doing. We are just trying to categorize whether it is a reverse fault, thrust fault, or normal fault here. Okay. And these faults are which are associated with the magnitude greater than 6. Okay. Now, these faults range from regional, okay, example for seismic hazard assessment, to local. Okay. These studies actually, okay, the studies usually range from that. This is for the design parameters. So, you may have, for example, you have a map here, okay, and then your active fault is passing through this area over here like this. So, you can have a regional scale studies also, but the local, or we can say site specific studies should be done, okay, if you have plans for the upcoming engineering projects. Okay, that can be done, and that is your local scale. So, here you can do sort of the detailed mapping, and then so mapping can be done, okay, and then or you can do the paleoseismic studies. And this will be your, we can say, local or site specific studies. Okay. So, in both the cases, the input of paleoseismic data come from the detailed site specific studies. Okay. And that's what I was talking about, the detailed trenching and mapping of the active faults. So, this too you will have to do if you want to say that this is an active fault. Okay. Just doing the geomorphology part, maybe to some extent we can say that will be in preliminary interpretations. But finally, if you have to have the detailed information for the site specific, because you need to have the design parameters and all that, based on how much will be the ground shaking, what will be the magnitude, how much will be the slip which is expected on that fault, that you have to do at the local scale. Now, such studies are conducted mainly to satisfy the regulatory statute, and especially in more or thickly populated areas with high rate of seismic activities. So, such areas are there in India at various locations, okay, and that part we have discussed in previous lectures. So, this has to be done when you have to, we are talking about the active faults. So, now if we, as we discussed, that if you need to characterize this, okay, whether it is active, capable or potential active faults, and that has been done because you have a regulatory statute commonly include specific language that defines the active faults. You can do that, okay, for different regions also, and in India we have various lot many languages have been spoken, so you can have those information available in that language. Okay. So, the following terms are most commonly associated with seismotectonic structures. Usually we use faults, blind thrust and fault related folds. Okay. Now, active characterized by current activity. Okay. So, if you have the current activity, and as we have seen the definition of the active faults also, that the activity has remained alive since last 10,000 years. Okay. That is one point, and we see that this fault topography is very active, and based on the paleoseismic studies we can suggest that the earthquake can be hosted on that fault or hosted by that fault in near future. Okay. So, active characterized by current activities, and active fault, that is one demonstrating current movement or action. So, this is the definition of what is the current, we can say contemporary historical during the Holocene or Quaternary times. Okay. Quaternary of course is a larger time span, we go up to like almost 2,000,000 years, but mostly we say that okay fine, these are Holocene, then they are active faults. Okay. Capable, having ability. Okay. A capable fault, that is one having ability for the movement. cannot most properly oriented faults be capable under certain stress regime. So, in some stress regimes they may not be very effective in the sense in terms of the movement. Potential again capable of being or becoming potential. So, we may see some activity, but that activity is been not very prominent throughout, not continuous, then we may say that this fault is having the potential of becoming active fault. So, this definition is very much similar to the capable one, because that what we are seeing, that it may having the ability to host the earthquake. So, just keep in mind the slide which we discussed previously about the active fault, that it is in 10,000 years and likely to host the earthquake in near future. Now, let me just have a brief discussion on the surface manifestation of earthquake. And this photograph was been taken by Dr. Kota in 1893, and that was after the earthquake of Nobi earthquake of 8 magnitude, and that was in 1891. So, fault scarp is over here, but if you have not passed on this information to the regulatory bodies, and if you have not set up norms that no construction will be done across this, then it is okay. But if that has been somewhere forgotten, or maybe it is not been implemented, then it is dangerous also. So, I just want to have couple of pictures which were been taken by different scientists in Japan after a span of maybe 10 years or so. And so, what people, local people also forget, and even the government also forget about that. So, this was the picture again that was taken in 1893, and scarp is over here. So, this is your fault scarp which we were talking in the sketches also. So, this is an, of course, this is an strike slip, plus you have the normal component. So, fault runs through this line over here at the base. So, fault runs like this here. So, further if we look at, then for this was the photograph by Shiko in 1891, immediately after the earthquake, and this was later on in 1969. So, what is this? What are the similarities here? This hilltop you can see properly, this one here and this one here. So, what has happened is that there is an after the erosion, and you have this fault scarp which is running like this over here, or the fault which is running like this, and this is your fault topography. So, road has been constructed. Now, let us see further, because as the time passes, the erosion will modify the scarp. At the same time, the human activities, so anthropogenic activity can also modify this type of evidence. So, this was in photograph. The previous one was in 1969, and this photograph is in 1974. So, 1974 also you can see the scarp over here. This is the scarp. Again, the photograph has been taken from the same angle. There is some construction which came up, and finally, the 1991, if you see, so this structure is sitting exactly on the fault. So, if you have not passed on or formed any norms, then such mistakes can be done, and this is from Japan. So, the earthquake was almost like 1891. If you see this one here, 1891, and the last photograph you are having 1991, okay, almost 100 years apart. Okay. So, still the scarp is there, but of course, people have forgotten and people have constructed the structures over there. So, in future the structure will be damaged. Okay. So, one has to be very careful in providing the information to public, to the urban planners about the active faults. Okay. So, we will stop here and we will have more discussion in the coming lectures. Thank you so much. Namaskar.